our final example is y double prime plus 4y is equal to sine of t plus h of t minus pi times sine of t minus pi. Let's look at what that function looks like. So here we have in Desmos, it says sine of x plus h of x minus pi times sine of x minus pi. And you can see essentially we have sine of x between 0 and pi. And then the effect of the h of x minus pi, sine of x minus pi, is to turn off that sine of x. And then we're going to have just 0 after x equals pi. So we want to understand how does this system behave if we give it a forcing term of sine of t, essentially for half of a period, okay, between 0 and pi, and then we're going to turn off that forcing term. Let's look at the Laplace transform of both sides of this differential equation. So that's s squared y minus sy of 0 minus y prime of 0. That was the Laplace transform of y double prime. Plus 4 times the Laplace transform of y is going to equal the Laplace transform of sine t, which is 1 over s squared plus 1, plus the Laplace transform of h of t minus pi, sine of t minus pi. That is going to be an e to the minus pi s coming from the heaviside function of t minus pi. And then we're going to have just the Laplace transform of sine of t, which we already know is 1 over s squared plus 1. Let's go ahead and plug in our initial conditions. Y of 0 is going to be 0. Y prime of 0 is going to be 0. So essentially, this system starts at rest, at 0. So we have that s squared plus 4 times y is going to equal 1 plus e to the minus pi s all over s squared plus 1. We can solve for y so that y of s is actually 1 plus e to the minus pi s over s squared plus 1, s squared plus 4. So let's let's take out the 1 plus e to the minus pi s. And then using partial fractions, we're going to want this to look like a over s squared plus 1 plus b over s squared plus 4. So that tells me, using the partial fractions, that we have a times s squared plus 4 plus b times s squared plus 1 is equal to 1, and then of course there's a 0s squared. Again, with these coefficients, I used a and b. I didn't use as plus b and cs plus d, and that's because there are no single s terms, so I knew that it would work out that the only non-zero coefficients would be the constants a and b. So multiplying this out, the coefficients of s squared are a plus b, and they have to sum to 1. Or sorry, they have to sum to 0. So b in this case is minus a. And then the coefficients of the constants, we're going to get that 4a plus b is equal to 1. Of course, b is minus a, so 4a minus a is 3a, which is going to equal 1. And so a is going to be 1/3, b is going to be minus 1/3. So we can rewrite y of s as 1/3 times 1 plus e to the minus pi s. So here I'm just going to go ahead and factor out the 1/3 to make my life easier. Then I'm going to have a 1 over s squared plus 1, and then minus a 1 over s squared plus 4. So we're going to find the inverse Laplace transform to essentially solve at the end. So that's going to be a 1/3. Okay, now my first term is going to be 1 times 1 over s squared plus 1. So if I take the inverse Laplace transform of 1 over s squared plus 1, that's going to give me a sine of t. And now my second term is going to be the e to the minus pi s, again, times this 1 over s squared plus 1. So when I take the inverse of the Laplace transform with the e to the minus pi s there, I'm going to have a heaviside function of t minus pi. And when I take the inverse Laplace transform of 1 over s squared plus 1, it would normally be sine of t, but because of that e to the minus pi s, it's sine of t minus pi. Now, if we want to look at 1 over s squared plus 4, that's not quite in the right form. I'm going to divide that by 2 and then multiply by 2. And that will allow me to look at the inverse Laplace transform of that term, which is going to be a minus 1/2. This is, of course, going to get multiplied by 1. This whole thing is going to get multiplied by 1 here. And so then when I look at 2 over s squared plus 4, that has this kind of form of a over s squared plus a squared. And that is the Laplace transform of sine of at. And so when I take the inverse Laplace transform here, I'm going to get sine of 2t. Okay. Then finally, the last thing is again, I have a minus 1/2, but now I'm going to multiply e to the minus pi s times this. And so now there's going to be a heaviside function involved. And so I'm going to get the heaviside function of t minus pi times the sine of, should be the sine of 2t, but instead of t, we're going to have a t minus pi. Notice that the t minus pi is in parentheses. So I would have had a sine of 2t, but now it needs to be the sine of t times, or sorry, the sine of 2 times the quantity t minus pi. And that is my solution to the differential equation. We can look one last time at the plot in Desmos. So here we have the forcing term and then the response. Okay, so notice that I'm going to go ahead and show you the solution. So notice that the behavior between 0 and pi is just a small kind of sine curve looking function there, right? But then after t equals pi, we get a different response when we then turned off the forcing term. So we get this different response there.